Next topic, interesting one, limits at infinity. The basic idea here is, what if within a limit we let x go to infinity? We let x get as big as it wants, or even as negatively big as it wants. We can go to negative infinity. So I want to start this one with a quick example, y equals 1 over x. And I hope you know what that looks like. That is a hyperbola. So quick sketch here, whoop, whoop. And the bigger x gets, the smaller y gets, and it'll get as close as I want to 0. Bigger and bigger and bigger goes x, smaller and smaller and smaller goes y, but it is never actually 0. It's just going to approach this line, y equals 0. Okay, and I hope you know, or it sounds familiar, that is a horizontal asymptote. It's getting closer and closer, as close as I want even. And so in this case, we'd write the limit as x goes to infinity of 1 over x is equal to 0. And you'd be surprised how often it's incredibly useful to have a language like this that says, okay, I've got a circuit. In the long run, what will the voltage be across some gap? And the long run for electricity might actually be a few seconds, right? But it stabilizes in the end. Or I have a population of deer or bacteria. Okay, in the long run, what is this full capacity that that population might reach before they run out of food, say, or they stabilize to some number? So this language of limits at infinity is really talking about equilibriums usually. And equilibriums show up all the time. And a language for them to talk about them precisely is incredibly useful. So let's try to make this a bit more precise. Here we are in this beautiful definition. It's a little bit loose, but good enough for us for now. It says the limit as x goes to infinity of f of x equals L. So in this case up here, f is 1 over x, and that L would be 0. This means that f can be made arbitrarily close, that is, as close as you want to L by making x sufficiently big. So in this case up here, if I wanted y, or f of x, to be within 1/1,000,000th of 0, I just have to make sure that x is bigger than 1,000,000. And you go, you know what, that's not close enough. I want you to ensure that x is going to be within 1/1000,000th of 0, a very, very tiny margin of error. And I say it will always be that close as long as x is bigger than 1,000,000,000. And we could play the same game going to the negative side. Okay, so that's what it means to have a limit at infinity. For that limit to exist, it means that basically that y value stabilizes. It gets closer and closer to something, or it can even reach it too, but it can't go away from it. And in this case, we call that line y equals L a horizontal asymptote. Hopefully a familiar word. A word maybe you've seen but never got a real definition for, and this is a real definition that you had to wait until calculus to hear. All right, enough talk. Let's just do a couple of real basic examples here. I want to find all of the horizontal asymptotes of a couple of not too tricky functions. So 1 over x. We just saw that if I take the limit as x goes to infinity of 1 over x, that is 0. And that's going to give us the asymptote y equals 0. Oops. My box went around the wrong way. But you might not realize I should also check the left side. What happens as x goes further and further to the left? And to write that down, I'm going to say negative infinity. And I can get another horizontal asymptote. Sorry, make this an equal sign. Another horizontal asymptote, in this case, is also 0. We get the same one in both cases because as x goes to negative infinity, it's going to be smaller and smaller negative numbers. And so this is also y equals 0. We probably don't need to write it again. But the point here is that we need to check both directions. Okay. So thanks to some limit laws, we can also play the same game with slightly more complicated functions. In this case, on 2, the limit as x goes to infinity of 2 over x minus 3 plus 4 I can actually just separate this out and say this is the limit as x goes to infinity of 4. Okay, thanks, limit laws. Doing these separately, there's a little trick here. As x goes to infinity, this 2, well, the 2 is just going to 2. Nothing special is happening there. X minus 3 is going to infinity, and this 4 is going to 4. And you'll see me playing this little arrow game a lot. It's just sort of a way of showing my work or showing my thought processes when I don't want to do anything more complicated. So 2 over infinity, in this case, a constant number over infinity, or a constant number divided by larger and larger and larger numbers, this whole thing is going to go to 0. Plus, 4 doesn't care what happens to x. So 4 is just going to stay a 4. Okay. All right, so a couple lessons here. When you've got lots of parts, you can often split them up thanks to our limit laws, but also we can kind of think through what happens to numerators and denominators separately. So a non-zero constant divided by something going to infinity, that's always going to go to 0. Okay. In this case, our actual answer, I should write out more formally, is y equals 4. So again, the left and the right have the same asymptote. I'm going to let you go ahead and do the left side on your own, but you should check that if this goes to negative infinity, nothing changes. All right. But let's go ahead and show you an example that you should be familiar with, if you're not already, and that will give us two different limits on the left and the right. E to the x, we'll do a real quick sketch here to remind you. E to the x should be getting familiar to you. It looks a little bit like this. Ooh. It actually goes very, very fast off to the right. And so you should be looking and saying, okay, to the right, something very different is happening than when I go to the left. And a quick sketch is a wonderful way of making sure that you get reasonable answers out. So let's do both of them then. The limit as x goes to infinity of e to the x. All right, e to bigger and bigger and bigger powers is going to get as big as you want. Big without end, and it's not going to come back down. So this thing we're just going to say is infinity. Okay? And you can just know that from now on too, right? That this thing is going higher and higher and higher without end. We don't need to show a lot of work in this case. Let's go ahead and do a little bit more work as we go off to the other side. Oh, I should stop and say there is no asymptote here on the right. So we write that limit equals infinity, but we don't write that there's some magical asymptote y equals infinity. That doesn't make a whole lot of mathematical sense. But as I go off to the left, we get something else. Maybe you can kind of tell from the picture or your knowledge of e to the x what should be happening here. I'm going to go ahead and do a small trick to help justify this some more. This is the same as the limit as x goes to infinity of e to the negative x. Okay, so rather than letting x go to infinity, we have x go to negative infinity, we have negative x going to, I guess, negative infinity in this case. Hopefully that makes sense. Okay, if you need even a little bit more help, and I don't need you to show all of these steps in the future, but it's worth thinking through once or twice, e to the negative x is the same as 1 over e to the x. And this, the top, is going to 1. The bottom, as we saw before, is going to infinity. 1 divided by infinity in this case, or 1 divided by bigger and bigger numbers, is going to get as small as you want, as close to 0 as you want, so this whole thing equals 0. So we get the beautiful asymptote, y equals 0. Nice. And that's what we expect from this picture too. So e to the x grows very, very fast going to the right, and actually approaches 0 very, very fast going to the left, and is never negative. Okay, neat. Those were some basic examples that I don't need you to show a whole lot of work for in the future, but it's worth kind of seeing once or twice. However, what if we have something a little bit more complicated here, like these two amazing functions here. And what I'd like to do is show you a technique that can be pretty darn helpful in dealing with kind of quotients, divisions of things. So what I'm going to do is this amazing algebra trick which says I'm going to multiply the top and the bottom by the same thing. And what I'm going to multiply them by is 1 over x squared. Why x squared? I just picked the biggest power on the top or the bottom. And why we're doing this is to hopefully cancel out some of these powers. So if I do this correctly, I should get this limit as x goes to infinity of 5 minus 1 over x over 4 minus 3 over x, applying this 1 over x squared to every single term inside. Now this is true as long as x doesn't equal 0. Right? I can do this as long as I'm not secretly dividing by 0. But this limit is at infinity, and that's nowhere near 0, so this should be totally safe. Okay, so now we let x go to infinity, and we say this thing is going to 0, this thing is going to 0, this is going to 5, this is going to 4. What am I left with? 5/4. Incredible. Right. Neat technique, dividing the top and the bottom by the same thing. Hopefully what should then become really clear is that all that matters is your biggest powers. It's really just a battle of the biggest powers to see who wins or by how much. In this case, it's the same exponent, and so we end up with these two coefficients hanging out. Kind of a neat thing about rational expressions. All right. Lots of variations on this. This is the simplest form, but let's go ahead and up the ante a little bit. Upping the ante is a poker metaphor, but it means to make it a little bit more serious or complicated. In this case, where I have a square root involved, I want to do the same thing. So let's just go ahead and say, all right, the biggest power on bottom is an x. So let's go ahead and again, we'll multiply everything by 1 over x to try to get rid of that x. This time I'm going to negative infinity. I'm not going to have a big difference here. So on bottom, I get 3 minus 5 over x. Just dividing everything by x. But what happens with that square root? And here is the trick. I can divide everything on the inside by, rather than x, inside of the square root, it becomes x squared. 2x squared plus 1. Okay. To bring it into the square root, I need to square it, so that if I were to bring it out of the square root, it would come out as an x. And I'll give you another quick example of this in a second. Let's go ahead and clean this up a bit more. This is the limit as x goes to negative infinity of the square root of 2 plus 1 over x all over 3 minus, let's go ahead and make that a 0. Because in the limit, 5 over x is going to be a 0. This is going to go to 0. Looks like I get the square root of 2 over 3. By my standards, that's actually a beautiful number. Neat. Okay, so the one element here that usually needs a little bit more practice is just to kind of clarify. If I had, say, let's pick some weirder numbers here, the square root of x cubed plus 5, and I wanted to divide by x to the 4th, this becomes, sorry, let's make this even weirder still. Let's make this the fifth root. Okay. Well, the question is, how do I bring in that x to the 4th into that 5th root? And the answer is going to be as an x to the 20. Whew. Why x to the 20? 4 times 5. Okay. And the real thing going on here is that this is x to the 4 to the 5, and then we're taking a 5th root, but a 5th root is just to the 1/5. A little weird to think about here, but that 5 and that 1/5 should be able to undo each other. However, this is x to the 20. 4 times 5, when we have those exponents, to the 1/5. Okay, take a second and make sure that that makes sense to you. That if I wanted to bring this x to the 20, out of this 5th root, it would come out as x to the 4th. All right, because those powers can really trick you up. Neat.